You've been lied to about atoms. Not maliciously, not intentionally, but fundamentally. And the lie isn't just wrong. It's so wrong that if you actually believed it, if you took it seriously, reality as you experience it would be impossible. Here's what I mean. Close your eyes for a second and picture an atom. What do you see? I'll tell you what you see. You see a little solar system, a nucleus in the center, maybe a few protons and neutrons clustered together like a tiny, dense ball. And then electrons, little planets, orbiting around it in neat circular paths. Maybe they're different colors in your mental image. Maybe they're moving. Maybe you even see those orbital rings, those shells we learned about in chemistry class. That image, that beautiful, intuitive, comforting image that every textbook put in your head, it's not just wrong. It's catastrophically wrong. And I don't mean wrong like, well, it's a simplification. I mean wrong like if atoms actually worked that way, you would fall through your chair right now. Your hand would pass through this screen. Matter as we know it couldn't exist. Think about that for a second. The most basic picture you have of physical reality, the image that underlies everything you think you know about how stuff works, is so fundamentally incorrect that if it were true, you wouldn't be here to think about it. So let me ask you, what's actually going on? What are atoms really like? And more importantly, why does the truth break every intuition you have about how things should work? Let's start with something concrete, something you can do right now. Take your hand, press it against the table in front of you, or the armrest of your chair, or the wall. Push hard. It doesn't go through, right? Obvious, trivial. Of course your hand doesn't pass through the table. That's what it means for something to be solid. That's what we mean by matter. Things are made of stuff, and stuff takes up space. And two pieces of stuff can't occupy the same space. So when you push your hand against the table, it stops. Except here's the problem. Your hand is made of atoms. The table is made of atoms. And atoms, actual atoms, not the little solar system cartoons, are almost entirely empty space. How empty? Let's put some numbers on it. The nucleus of an atom, where essentially all the mass lives, is about 1 femtometer across. That's 10 to the minus 15 meters, a millionth of a billionth of a meter. If you scaled up an atom to the size of a football stadium, the nucleus would be a marble sitting at the 50-yard line. And the electrons? In that same stadium-sized atom, you wouldn't find the electrons anywhere. You couldn't find them. They don't have locations. Not really. They exist as probability clouds, smeared out waves of maybe here, maybe there, that extend throughout the entire atom and beyond. So when you press your hand against the table, you're pushing one cloud of mostly empty probability against another cloud of mostly empty probability. And somehow, they refuse to overlap. They push back. They feel solid. Why? And don't say, because electrons repel each other. That's true, but insufficient. Electrons do repel. They're all negatively charged, and like charges repel. But that electrostatic repulsion, that's not what's keeping your hand from passing through the table. If that were all there was to it, the electrons could just redistribute, move out of the way, find configurations where they minimize the repulsive energy while still letting the atoms interpenetrate. The reason your hand doesn't fall through the table has almost nothing to do with electrostatic repulsion. The real reason is something far stranger. Here's where most explanations go wrong. They'll tell you about the Pauli Exclusion Principle, like it's some kind of rule that electrons follow. Like electrons are well-behaved little entities that check a rule book and say, oh, I can't go there. That quantum state is already occupied. That's not what's happening. The Pauli Exclusion Principle isn't a rule electrons obey. It's a statement about what electrons are. Let me explain this carefully because it's crucial. Electrons are fermions. Fermions are particles with half-integer spin. Spin 1/2 in the case of electrons. And there's a deep mathematical fact proven by Wolfgang Pauli in 1925 and connected to the fundamental structure of space-time by the spin statistics theorem. The quantum wave function describing multiple identical fermions must be antisymmetric under particle exchange. What does that mean in English? It means if you have two electrons and you write down the mathematical function that describes the quantum state of both of them together, and then you swap the labels on the two electrons, you exchange them, the wave function must flip sign. It must become negative. Now here's the kicker. If you try to put two identical fermions in exactly the same quantum state, same position, same spin, same everything, and then you swap them, you haven't actually changed anything. They were in the same state. Swapping them is meaningless. But the math says the wave function must flip sign when you swap them. So you'd need a wave function that equals negative itself. The only number that equals negative itself is 0. 0. The wave function is 0, which means the probability of finding that configuration is 0, which means it cannot happen. Not it's really unlikely. Not it takes a lot of energy. It literally, mathematically, fundamentally cannot happen. This is the Pauli Exclusion Principle. Two identical fermions cannot occupy the same quantum state. Not because there's a force preventing it, not because they repel, because the mathematics of what fermions are make such a configuration correspond to a wave function that doesn't exist. Okay, but we still haven't answered the question. Why doesn't your hand fall through the table? Because of this. When you try to push two atoms together, you're trying to bring their electron clouds into the same region of space. And if those electron clouds overlap too much, you'd be forcing electrons into the same quantum states, lower energy states, ground states, states that are already occupied by the other atom's electrons. And that can't happen. So the electrons have to go somewhere else. Higher energy states, excited states, states that cost energy. This is degeneracy pressure. It's not a force in the traditional sense. There's no force-carrying particle, no field pushing back. It's a quantum mechanical consequence of the Pauli Exclusion Principle. When you try to confine fermions to smaller volumes or force them into already occupied states, you have to promote them to higher energy levels. And that takes energy, a lot of energy. That energy, that cost, is what you feel as the solidity of matter. When you press your hand against the table, what you're feeling isn't atoms touching like billiard balls. You're feeling the universe refusing to let electron quantum states overlap. You're feeling the anti-symmetry of the fermion wave function. You're feeling the deep mathematical structure of identical particles. Everything you've ever touched, you've touched with geometry and exclusion rules encoded in the spin statistics theorem. Not forces, not collisions, statistics. Let's go deeper. You might be wondering, why do fermions have antisymmetric wave functions in the first place? Why is nature built this way? This is where Richard Feynman would lean back and give you that characteristic shrug. I don't know, he'd say. Nobody knows. We can prove it mathematically from the structure of quantum field theory and special relativity. The spin statistics theorem does exactly that. But as for why the universe chose this mathematical structure instead of some other structure, I can't tell you. The spin statistics theorem, proven rigorously by Pauli and later by Feynman himself and others, shows that in any quantum field theory that respects special relativity and locality, particles with half-integer spin must be fermions with antisymmetric wave functions, and particles with integer spin must be bosons with symmetric wave functions. It's not a choice. It's not a parameter you can tune. It falls out of the mathematics of combining quantum mechanics with relativity. But why does the universe obey quantum mechanics? Why does it obey special relativity? Why is space-time four-dimensional with one time dimension and three space dimensions, which turns out to matter for the spin statistics theorem? At some point you hit bedrock. You find principles that are just true, mathematically consistent, and empirically verified, but not explainable in terms of anything deeper. Maybe there's a deeper layer we haven't found yet. String theory tries. Loop quantum gravity tries. Maybe they'll succeed, maybe they won't. But right now, fermions have antisymmetric wave functions because of the spin statistics theorem is as far down as we can go. And that's why your hand doesn't fall through the table. Not because of forces, because of the fundamental mathematical structure of quantum fields in relativistic space-time. Now here's what's psychologically fascinating about all this. Why does the solar system model of the atom feel so right? Why is it so intuitive, so compelling, so easy to picture? Because it maps onto something you already understand. Gravity. Planets orbit the sun because of gravity. The sun pulls. The planet has momentum. You get an ellipse. It's Newtonian mechanics. You learned it. It makes sense. It connects to your experience of throwing balls and watching them arc. So when someone says atoms have electrons orbiting a nucleus, your brain slots that right into the gravity folder. It feels explanatory. It feels like you understand it. But atoms aren't held together by gravity. They're held together by the electromagnetic force, mediated by photons, described by quantum electrodynamics. And in the quantum realm, nothing orbits. Electrons don't have trajectories. They don't have paths. They exist in superpositions of states until measured, described by wave functions that evolve according to the Schrödinger equation, or more accurately, the Dirac equation, which includes relativity and spin. The reason the solar system model feels intuitive and the quantum reality feels bizarre is that you've never experienced quantum mechanics directly. Your brain evolved to model medium-sized objects, moving at medium speeds in medium energy environments. Rocks, predators, prey, tools. None of those require quantum mechanics to predict or understand. So quantum behavior, superposition, entanglement, exclusion principles, feels weird, unnatural, hard to visualize. But here's the thing. Quantum mechanics isn't weird. It's fundamental. It's the most accurate theory of physical reality we've ever developed. Quantum electrodynamics predicts the magnetic moment of the electron to 11 decimal places. 11. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. The weirdness isn't in the physics. The weirdness is in the gap between your evolved intuitions and the actual structure of reality. Let's make this concrete. Let's talk about what happens when you really take the Pauli Exclusion Principle seriously. White dwarf stars. When a star like the Sun runs out of fuel, it collapses. Gravity pulls everything inward. Normally, thermal pressure, the random motion of hot particles, would push back and stop the collapse. But once the star cools and the thermal pressure drops, what stops it? Electron degeneracy pressure. The star collapses until the electrons are squeezed so tightly that they're being forced into higher and higher energy states by the Pauli Exclusion Principle. The pressure from this, the sheer quantum mechanical refusal of electrons to occupy the same states, holds up the entire star against the crushing force of gravity. A white dwarf is essentially a single quantum object the size of Earth, held up entirely by the Pauli Exclusion Principle. The same principle that keeps your hand from falling through the table keeps a stellar remnant from collapsing into a black hole. Same physics, different scale. And if you add more mass to a white dwarf, if you push it past about 1.4 solar masses, the Chandrasekhar limit, even electron degeneracy pressure isn't enough. The star collapses further. The electrons get forced into the protons, forming neutrons through a process called electron capture. And now you have a neutron star, held up by neutron degeneracy pressure. Same exclusion principle, different fermions. A neutron star is matter compressed to nuclear densities. A teaspoon of neutron star material would weigh 1 billion tons. And it's stable for a while, because neutrons are fermions too, and they refuse to occupy the same quantum states. Push even harder, add even more mass, and eventually even neutron degeneracy pressure fails. Then you get a black hole. And at that point, we don't know what happens, because we'd need a theory of quantum gravity, which we don't have. But up until that point, everything is held up by exclusion, by antisymmetric wave functions, by the deep structure of fermions in relativistic quantum field theory, the solidity of matter, the stability of stars, the fate of the universe, all resting on the fact that identical fermions can't be in the same quantum state. Here's another way to think about it. The Pauli Exclusion Principle is why chemistry exists. If electrons were bosons instead of fermions, if they had integer spin instead of half-integer spin, they could all pile into the lowest energy state around a nucleus. Every electron in an atom would sit in the ground state, the 1s orbital, overlapping completely. There would be no shells, no orbitals, no periodic table, no chemical bonds, no molecules, no life. The entire richness of chemistry, the reason carbon can form 4 bonds, the reason oxygen is reactive, the reason DNA can encode information, comes from electrons being forced into higher and higher energy orbitals because the lower ones are already occupied. The exclusion principle doesn't just make matter solid, it makes matter interesting. It makes complexity possible. It makes you possible. And it all comes back to spin, to the half-integer spin of electrons, to the anti-symmetry of the fermion wave function, to a mathematical property of quantum fields that you cannot see, cannot touch, cannot directly experience, but which underlies everything you are and everything you perceive. Feynman had a way of putting this. He'd say, you can ask me why magnets repel, and I can tell you about magnetic dipoles and spin and quantum mechanics. But then you can ask me why those things are the way they are, and I can go deeper into quantum field theory, into the structure of space-time, into the symmetries of nature. But at some point, he'd say, I have to stop and say, that's just the way it is. That's what we've discovered. That's the pattern the universe follows. And the remarkable thing isn't that we can't explain it in terms of something more familiar. The remarkable thing is that we can explain it at all. That we can find mathematical structures, differential equations, field theories, symmetry groups that accurately describe how reality behaves at the deepest levels we can probe. The Pauli Exclusion Principle is one of those bedrock facts. Fermions have antisymmetric wave functions, period. That's what we've discovered. And from that single fact flows the solidity of matter, the structure of atoms, the periodic table, chemistry, biology, stars, galaxies, everything. One mathematical property of quantum fields, and the universe becomes comprehensible. So let's come back to where we started. You press your hand against the table. It doesn't go through. You used to think that was because atoms were like little billiard balls, solid nuggets of stuff that bump into each other. Now you know better. You know that atoms are mostly empty space. You know that electrons aren't particles in orbit, but probability clouds described by wave functions. You know that the reason your hand doesn't fall through the table has nothing to do with forces in the traditional sense, and everything to do with the antisymmetric nature of fermion wave functions under particle exchange. You know that what you're feeling when you touch something is the universe enforcing quantum statistics. You are feeling the Pauli Exclusion Principle. You are feeling the deep mathematical structure of reality. And here's the thing. This isn't some abstract theoretical curiosity. This is every tactile sensation you've ever had. Every time you've held someone's hand, every time you've felt the ground beneath your feet, every time you've gripped a pencil or caught a ball or leaned against a wall, all of it, every single instance of matter feeling solid is quantum mechanical exclusion translating into macroscopic experience. You've been touching quantum field theory your entire life. You just didn't know it. There's something profoundly beautiful about this. Something almost spiritual, if you're inclined that way. The universe doesn't owe us comprehensibility. It doesn't have to make sense according to our evolved intuitions. And yet, when we dig deep enough, when we set aside our assumptions and follow the mathematics wherever it leads, we find patterns, structures, laws. We find that the solidity of matter comes from statistics, that chemistry comes from exclusion, that stars are held up by the same principle that keeps your hand from passing through the table. We find unity, connection, deep structure, and we find that the most mundane experience, touching something, is actually a window into the fundamental nature of reality. You don't need a particle accelerator. You don't need a telescope. You just need to pay attention, to ask why, to refuse to accept that's just how it is, until you've gone as deep as current knowledge allows. Feynman understood this better than almost anyone. He knew that the goal wasn't just to collect facts, but to understand, to see the connections, to appreciate the profound strangeness and beauty of how the universe actually works, as opposed to how we think it should work. And he knew that real understanding feels different from familiarity. Familiarity is comfortable. Understanding is exhilarating. Familiarity lets you nod along. Understanding makes you stop and stare and think. Wait, what? So here's my challenge to you. The next time you touch something, anything, pause for a second. Think about what's actually happening. Think about electron clouds refusing to overlap. Think about anti-symmetric wave functions. Think about the Pauli Exclusion Principle, translating quantum statistics into the sensation of solidity. Think about the fact that you're not experiencing atoms as little solar systems, because atoms aren't little solar systems. You're experiencing the deep mathematical structure of fermions in quantum field theory. And then think about how astonishing it is that we figured this out, that a bunch of curious apes on a small planet looked at the world, asked questions, did experiments, worked through the mathematics, and discovered that reality is far stranger and more beautiful than we ever imagined. We discovered that matter isn't made of stuff in the way we thought, that solidity is an emergent property of quantum statistics, that the universe runs on principles we can describe with mathematics, but can barely visualize. We discovered that the most basic assumption we had about atoms, that they're like tiny solar systems, was so wrong that if it were true, reality itself would be impossible. And somehow, despite that, or maybe because of it, we kept digging, kept questioning, kept searching for deeper understanding. That's the real miracle. Not that the universe is comprehensible, though that's miracle enough, but that we refuse to stop asking why, that we're not satisfied with comfortable lies when uncomfortable truths are available. That's what Feynman taught us. Not the specific equations or principles, though those matter, but the attitude, the relentless curiosity, the willingness to follow the evidence, even when it shatters your intuitions, the commitment to understanding reality as it actually is, not as we wish it were. So touch something. Feel the Pauli Exclusion Principle. Feel the anti-symmetry of the fermion wave function. Feel the deep structure of quantum fields translating into macroscopic experience. And marvel at the fact that you can know this, that you can understand this, that the universe, for all its strangeness, is not beyond comprehension. You've been touching quantum field theory your entire life. Now you know it.